the talk, which is Rosa Malandrino from Institut d'Astrophysique de Paris, and she will talk about voids.
Thanks to the organizer for giving me the opportunity to present here. So I'm a PhD student at IUP. I'm about to start my third and last year. And I will tell you about this project we've been carrying out within the Aquila Consortium with these people about cosmic voids in constrained simulation. So it's worth reminding why voids are interesting. Since by definition they are the regional space where there's less dark matter, they are dominated by other components. So for instance, dark energy, which makes them the perfect environment to study cosmic acceleration, either by constraining models like dynamic dark energy, but also testing modified gravity. But for the same reason, they're also sensitive to the gravitational effect of neutrinos, which we usually neglect, but the massive neutrino actually leave an imprint in the properties of voids. And finally, since they are a relatively calm environment, they're not as affected by gravitational collapse as halos. So they preserve the information of their universe. So in principle, they could be used to constrain, for instance, and there are time capsule that allows us to look into the early universe. So they're very interesting for cosmology, but actually also for astrophysics, because for instance, the property of galaxies depend on the environment. So being able to differentiate what galaxies live in voids rather than in halos can teach us something about galaxy evolution. Okay, so how do we find voids? Well, historically, people would just look into this early surface and say, this is a void, and this is a void. But now, these days, surveys look more like this. So obviously we need to find another way to find them, but the reason why I'm showing you this plot is to illustrate the intrinsic challenges of void finding, which first of all, we observe voids through galaxies, which are biased tracers. So the voids we find in galaxies are not necessarily the same as the ones that exist in the dark matter distribution. But more importantly, we observe galaxies with instruments which have limitations, such as survey mass or magnitude limits. So for instance, you can see here, this line of sight and this line of sight, they're partially covered, so you don't really know what's going on here, and you lose a lot of volume. And for the same reason, when you reach the edges of the surveys, you might think some region is empty, but in reality, you just cannot observe the galaxies because they're too faint. So is this just an observational problem? What if we knew all the galaxies in the universe with 100% certainties? Well, we still have some problems because there is not a unique void definition. You can start from the same distribution of dark matter or tracers, and based on the definition, you end up with something very different. So here I put a quote from this paper, constructed the local void, say boundaries can be arbitrary and will undoubtedly be a source of contention. So there is not a unique way of defining void. And finally, we have only one realization of the universe, but we know that the large-scale structure emerges from a statistical process, so we would like to be able to quantify the uncertainties. So what we propose here is a statistical method to detect high significant voids and determine their properties in a Bayesian framework. And this framework is called Borg. I don't have the time to explain the details, but the basic idea is it's a large probabilistic engine that samples initial conditions and updates them based on how likely they are to match the observed galaxies at present day. So to show an example, we start with galaxy position. Here I just illustrated the region where we have a lot of galaxies. We pass this to Borg and we obtain a set of possible initial conditions that might have generated these galaxies. And then we can use those to pass to an n-body solver to get the realization of the large-scale structure at present day. And it looks a bit like this. I'm not sure you can see it, but for instance, this structure is the same here, this filament, so we're actually doing things right. Inside the circle, of course, because outside we don't have data to constrain the large-scale structure, so it's basically random. And this is even clearer when you plot the average of this statistical realization outside. It's almost uniform. But here, and here, we have information, we have voids, so we want to characterize those. I'm working with the void finder called BID. To put it simple, it starts with discrete tracers, computer-borne isolation to estimate the density, and then merges this tracer with what's called a watershed transform. So the result looks a bit like this, which is a complicated shape, but as a first approximation, you can think of it as a center and an effective size. So when you run this void finder on all this realization, you find voids that look a bit like this. And although it might look messy, like there is not stable structure after all, if you overlap these points on the same space, you find that there are some regions that are more likely to be identified as voids than others. So there is a signal here, and it actually matches the voids in the average, for instance, here. So we want to characterize these clusters of points, which is a classical detection problem. But the question is, how many points make a cluster significant? Because, okay, the ones I pointed are pretty solid, but what about this? What's the threshold that makes a cluster significant? But thankfully, we have the outside of the box that, as I said, the points are randomly distributed. So we can count the occurrence of clusters of 1, 2, 3 points to see how likely they are to appear just by random chance. And it turns out that the distribution is Poissonian. So we can associate to n the members of a cluster a probability. So we decided to enforce a 5 sigma detection threshold and accept only the clusters that are very, very unlikely to appear just by pure chance. And these are the ones that pass this criterion for this example. So at this point we're done, right? Because we have samples of the same statistical void, and we just need to combine them to infer the properties. So we end up with the probability distribution of the center. So we don't have just a center for the void, but actually a cloud of position where it could be, and also some probability distribution for the radius. So if you want to visualize this void, we can take the average of the two distribution and you end up with spheres that, as you can see, occupy the space around us. We're in the center of this plot in a non-overlapping way. But we can also project these spheres into the sky and overlap with the galaxies that were used to obtain the large-scale structure simulation. So the first thing to notice is that they actually occupy the empty spaces that you would recognize by eye as voids. But since this plot is in galactic coordinate, you can see that there is the galactic plane here. And we do find voids in a region that we don't observe. So this shows the power of work to reconstruct the large-scale structure from incomplete data. Okay, this is very nice, as I said before, voids are not actually spheres. So here is what the samples look like, where the red circles are a representation of the Bernoulli cells. So to actually get an idea of the shape of the void, we can overlap these cells on the three-dimensional space and count how often a point is likely to be inside a void rather than not. So you end up with something like this, where the purple represents the outskirts that are sometimes counted as void, but more often not. And the yellow is the very deep interior of the void. So this is too big compared to the sphere, which represents the statistical volume. So we need to cut it in order for the two volumes to match. And you end up with something like this, which yields the same statistical result, but you actually have information on the shape. So to actually validate this shape, we compare with the dark matter distribution that we use to extract these voids. And in this plot, I'm showing in a way marginalization over the z-axis of the shape of the void, overimposed to a slice of the density field. So you can see that it's good overall, but this plot lacks a bit of three-dimensional information. So it might be more useful to show slices over z. So you can actually see the relation between the shape of the void and the local environment. And this is very good. It almost looks like a drawing by hand, and I promise I didn't. So we're doing things right. So we can repeat the same procedure for all the void, and the overall catalog looks a bit like this. Unfortunately, I cannot show this interactive plot, but if you go on this website, you can move around and play with it, which gives the information of what the local neighborhood looks like. So this is nice, but what do we do with it? As I said, you can learn astrophysics from it, but since we're interested in cosmology, we can do a couple of things. First of all, the usual void summary statistical methods, for instance, like the Alcoba-Simpson effect, cannot be used in this case because we obtained the simulation with an assumed cosmology, so we just get the same result. But what we can do is correlation, so we can either use intergravitational lensing, because the light interacts with the large-scale structure, so there should be a correlation with voids, or for CMB correlation, either with CMB lensing or the C effect or ISW. So we're still exploring possibility, but if you have ideas, please let me know because we're open to collaborate. So yeah, I conclude here. The novelty of this catalog is that we are picking the voids that we consider high significance, so they're likely to be real. So we bypass the problems of surveys like obscure line of sight or spurious voids, for instance. And we have a statistical way to assess the uncertainties. And also these voids are very well localized, so there's a well-defined center of boundaries, which makes them useful to use for density environment estimation. So you can use it for either a statistical application like galaxy evolution, but there are many more that I'm probably not aware of, or for cosmology with the cross-correlation analysis. So the next step, which is actually ongoing, is that in the Aquilon consortium, we're producing the same constraint simulation on bigger volumes, namely with the constraints from the SDSS. So we will be able to get even more voids and more statistical plot. So here, if you find animation, and here is the.
Thank you, Rosa, very much. Start there.
Very much. Very good. One question I wonder is, as was sort of discussed previous session, is there's lots of void finders, right? And using one of them, yes. How robust will the results stay to different kinds of void finders? Are you biased to this particular one that you've chosen?
So we didn't try other void finders. Our intuition is that the peculiarity of individual void finder will be kind of absorbed in the statistical process. So we expect the statistical result to be the same, but yeah, we didn't try it. So like when you plot this kind of cloud, you should think of it as a big void, not a sort of void. While for the probability distribution, I think this is more robust than shares of.
Very nice talk. I was wondering, are you including redshift-based distortion effects, especially figure of void things, looking at cross correlations maybe? So
this is actually what's going on in Borg. So I didn't produce the posteriorization, but yeah, when we basically use the permission condition, we evolve them with the proper simulation. And then when you put the galaxies, there's an appropriate bias model, but there's also a redshift distortion. And
not including figure of void.
Sorry?
Not including figure of void.
Don't think so.
You would have to resolve really the internal dynamics because
I think it would, because the simulation would have the
basis is to RPT.
The first simulation is PM plus quality.
Okay, but still you need to resolve the full internal structure of the.
we have some
discuss all.
Yeah.
Before you.
Okay. No more questions then. Thanks, Rosa, again.